In the previous section, we showed that ray tracing diagrams are very useful in determining the location and properties of images formed by spherical mirrors. However, for a more accurate description of the image and its location, we need a more analytical technique. We can apply the law of reflection at the surface of the mirrors to derive two equations, known as the mirror equation and the magnification equation, which provide the relationship among the following quantities: the focal length, the object distance, the image distance, and the magnification of the mirror, which is the height of the image divided by the height of the object. Consider the image of an object formed by a concave spherical mirror as shown in the figure. The two shaded triangles in the figure are similar, since they have equal angles. Therefore, the ratios of their corresponding parts will be equal. We see that HO over minus HI is equal to DO over DI. The minus sign appears in front of HI since the image is inverted. If we now consider another ray coming from the object, say the one that first passes through the focal point and then upon reflection comes out parallel to the principal axis. Here again, the two shaded areas represent similar triangles, provided the ray remains close to the axis. Equating ratios of corresponding parts, we get the following: HO over minus HI equals DO minus F divided by F. Setting these two expressions equal to each other and rearranging, we arrive at the relationship known as the mirror equation. This was derived for a real image formed in front of a concave spherical mirror. In this case, DI will be a positive number. However, if we have the case of a virtual image forming behind the mirror, then DI will be negative. By rearranging the first expression, we have that M is equal to HI over HO, which equals minus DI over DO, which is the magnification of the image. If M is greater than 1, the image is enlarged. If M is less than 1, then the image is reduced. If M is positive, then the image is upright with respect to the object, and if M is negative, then the image is inverted with respect to the object. The mirror and magnification equations can also be applied to convex spherical mirrors, provided that the focal length f is taken to be a negative number. The following reasoning strategy summarizes the sign conventions that are used with the mirror and magnification equations. They apply for both concave and convex mirrors. The focal length f is positive for concave mirrors and negative for convex mirrors. The object distance DO is positive for an object that is in front of the mirror. This is known as a real object. The object distance is negative if the object is located behind the mirror. This is known as a virtual object. This situation may arise in systems with two or more mirrors, where the image from the first mirror becomes the object for the second one. The image distance DI is positive for images that form in front of the mirror, which means on the same side of the mirror as the object is. This is a real image. The image distance is negative for images that form behind the mirror, which means on the opposite side of the mirror as the object is. To find the location of this image, the reflected rays will have to be extrapolated back behind the mirror. Thus, this image is virtual. Finally, the magnification M is positive if the image is upright with respect to the object. For this to occur, the image distance must be negative, which means the image is virtual. Therefore, virtual images are upright with respect to the object. If M is negative, then the image is inverted, or upside down, with respect to the object. For M to be negative, the image distance must be positive, which means a real image. Therefore, real images are inverted with respect to the object.